Okay, welcome to the last video in our renal lesson on general transport and organic transport of organic molecules. We'll talk a little bit about peptide reabsorption, and then we'll spend some time talking about urea, which is a very important molecule in the process of renal function. So first of all, peptide reabsorption also from the proximal tubule, okay? And notice that although large proteins are not filtered, okay, and that is the vast majority of the protein in the plasma, albumin, globulin, fibrinogen make up a large proportion in terms of percentage. And these are not filtered, but small proteins, peptides and such, like angiotensin and insulin and such, actually are filtered, okay? And in fact, they're freely filtered. So these need to be reabsorbed. At least, you want to retain the materials. So generally speaking, what happens is these are reabsorbed as amino acids. So you can retain the amino acids and not lose them. Amino acids are freely filtered, the peptides are freely filtered, and these are reabsorbed often through an amino acid sodium symport across the apical membrane. What usually happens with the peptides is that they're broken down into the amino acids. They're either taken into the cell via endocytosis and broken down, and then the amino acids are transported into the interstitium and then into the capillaries, or some of them are actually degraded by peptidases that are tethered to the apical membrane, and then the amino acids are reabsorbed from there through transcellular transport mechanism. Okay? Either way, remember there is normally no protein in the urine. So similar to glucose, if you see glucose in the urine, that's bad. Ordinarily, you don't find protein, significant amounts of protein in the urine. If you do, that means that there's a problem, and it's something that needs to be addressed, okay? So proteins are either not filtered or 100% reabsorbed, all right? So having talked about that, let's talk about secretion of organic anions and cations. And these are often secreted, which means we're not reabsorbing them, we're transporting them into the tubular lumen from the interstitium instead, okay? These may or may not be filtered. They are often, not always, but often bound to albumin and or other proteins. And if they are protein bound to something big like albumin, then they're obviously not going to be filtered, which means that secretion is really, really important, particularly for those organic substances, because that'll be the only way that you can get them from the capillaries into the renal tubule. They generally won't be filtered. So you should bear that in mind. Secretion, really important for getting rid of some of these substances that are actually normally protein bound. Okay? Some of these substances are endogenous, some are not. Here is a sampling of the endogenous, and a notable example is urate or uric acid, which is a result of purine metabolism. You get too much of it, you get gout. Creatinine, we've talked about a little bit in a previous lesson. That is a little bit secreted. We usually use it to measure glomerular filtration rate because it's not very secreted. Ideally, it would be filtered and neither secreted nor reabsorbed. It is a little bit secreted. But nevertheless, we still use it for GFR. Notice in terms of exogenous substances, PAH, an important one, that is really robustly secreted, so that effectively everything that enters the kidney is removed from the plasma and excreted in the urine, which means we can use it to measure or at least imply renal plasma flow. Penicillin, obviously an antibiotic, very common. Also secreted, and in fact it's secreted so much that you have to actually give enough to keep it above its transport maximum. Otherwise, it'll just be urinated out, and you won't be able to maintain an adequate plasma concentration to have an effect. So once again, it is also robustly secreted. Note that the secretion, again, occurs in the proximal tubule. We have active transport across the basolateral membrane and facilitated diffusion or sodium organic substance antiport across the apical membrane, so that makes that transport a little bit different than normal. Again, these transporters not very specific. They'll often transport more than one closely related substance. And again, recognize that the transport maximum is significant here. We are talking about transporters. So having done the peptides and some of our organic substances, let's talk a little bit about urea. Urea is it's a waste product of protein metabolism, so it's being generated all the time. It's a really special substance in renal physiology because it's a key to controlling water balance. And so we'll talk a lot about water transport in the next lesson, but I want to talk about the way that urea is transported here, and then we'll talk about how it's involved with water later on. Okay? So just as an overview, urea is freely filtered. So notice this 1 here, that's the level relative to the plasma. 1 means that it's the same level as the plasma, and because it's freely filtered, that should make sense to you. It's the same concentration here in Bowman's capsule as it is in the plasma in the glomerular capillaries. If it goes above 1, that means it's a higher concentration than the plasma. If it's below 1, then it's a lower concentration. Okay, so it's freely filtered. And then it's reabsorbed. 50% of it is immediately reabsorbed in the proximal tubule, okay? And then things get complicated. You actually have urea being secreted into the loop of Henle here in the renal medulla. And then it is reabsorbed again from the collecting duct. And we'll talk a little bit about this in more detail in a second. But you should notice these last 2 steps make for a urea recycling step where, and here is what I mean by that. So if we look at a single urea molecule and we trace it around, so it's secreted into the loop of Henle here, and then it's transported along in the renal tubule along with tubular fluid up the loop of Henle through the distal convoluted tubule into the collecting duct and down into the collecting duct. And then that same molecule can be reabsorbed into the renal medulla. And if it's reabsorbed into the renal medulla, then it can be picked up again by the loop of Henle through secretion and start that cycle all over again. So this is what we're calling urea recycling. It's a way to retain urea within the body rather than just losing it all out of the urine, okay? And you should recognize that that takes place. It's there to maintain the urea concentration there to help with water transport, which again, we're going to talk about later, all right? So, whoops. Okay, so notice that, okay, so our urea is freely filtered, excuse me, okay, right here, plasma level, level in Bowman's capsule equal to the plasma level. 50% is reabsorbed in the proximal tubule again, and then take a look at our concentration here on the bottom. We went from the same concentration as the plasma through the proximal tubule to actually a higher concentration than the plasma, and that's despite the fact that we lost 50% of our urea there. And that should tell you that what happened here is more water was reabsorbed in this segment than urea. So even though we lost 50% of the urea, we lost more than 50% of the water, and that actually raised the concentration of urea. So at the end of the proximal tubule, we're actually at a higher concentration than we were in Bowman's capsule. Okay, here's how that happens. As you'll find out soon, we'll give the details soon, sodium is reabsorbed in the proximal tubule. A lot of sodium is. And What that does is, because it's transported into the interstitium, it increases the osmolarity in the interstitium, and so water diffuses down at the concentration gradient from relatively high concentration in the renal tubule to low concentration and high osmolarity in the renal interstitium, okay? So we're losing water, okay? And as you lose water, that concentrates the urea. So what happens is urea diffuses down its concentration gradient, and it is paracellular, which means it's through the tight junctions, which aren't so tight in this area, okay? And it goes down from the lumen of the proximal tubule into the interstitium as well, okay? Down its concentration gradient, okay? And that's pretty much how this transport takes place in the proximal tubule, okay? So we have urea, a lot of urea being transported out in the proximal tubule, and that is through diffusion down its gradient paracellularly, okay? And now we have the addition of urea to the loop of Henle from the renal medulla here, right here through secretion, okay? And so we have secretion of urea, and that is also down concentration gradient, okay? The urea level in the medulla is always a lot higher than the plasma. So here is the urea concentration. As we go from the cortex to the inner medulla, you can see it increases a lot, okay? So a high urea concentration is maintained in the renal medulla, and then that makes for a high concentration on the outside of the loop of Henle relative to what's inside the loop of Henle. And so urea is transported down its gradient transcellularly into the loop of Henle. You should recognize this is a little bit of an exaggeration. These are urea concentrations when the hydration status is restricted. So if you're drinking a normal amount of water, it doesn't get quite this high. It levels off at about 400 or so, or a little bit below that. So recognize that this relationship quantitatively, not exactly spot on for a normal person with a normal hydration status. Nevertheless, the principle still holds. Huge concentration in the medulla, okay? So we have that transport going on, and now look, we went from 1.2 times the plasma concentration to 5.5 times the plasma concentration. So we've added a bunch of urea here, and we've increased the concentration quite a bit. So it's pretty high relative to the plasma in the distal convoluted tubule. And then the urea goes into the collecting duct, okay? And you'll notice that we go from 5.5 in the distal convoluted tubule, 5.5 times the plasma, to 25 times the plasma concentration in the urine when it's excreted. And the reason for that is because a lot of water reabsorption takes place in the collecting duct. In fact, this is where it's regulated. So the collecting duct is where you determine whether you're going to have a dilute urine or a concentrated urine. And again, we'll talk about that later, but you should recognize that we're losing water here. And as you lose water, the concentration in this collecting duct goes up. And because the concentration in the collecting duct is going up, and it's really tremendously high, we have a high concentration of urea here relative to the renal medulla. Now, the renal medulla is high, but it's not 25 times the plasma. It's more like 10 times the plasma or something. So you have a concentration gradient. So once again, urea being transported from high concentration to low concentration, again through a uniporter, transcellularly, back into the renal medulla. And of course, this is our urea recycling, where you can get reabsorption here, secretion of the same molecules here, and then a cycle where you get secretion, reabsorption, secretion, reabsorption. Okay? All right, so that is the end of our lesson here, and I'll see you guys in the rooms.